Boys, I thought I'd just present these ones slightly differently. I guess it's a bit easier for me in that I've got these, obviously the solutions here, and just draw your attention maybe to key elements of it. Obviously with question 12, we just got to use our U substitutions. I think we're getting used to the process. We just, I guess, changing the terminals to make sure they match off. The little negative a half there, we sort of make sure we bring it into everything. Just pay attention to detail. So C was there. 13 was really interesting. You solve it on the CAS and it gives a really, really different sort of answer. So I guess you could have a play around with it and try and work out how to factorise it into a format that they've got. And I guess that's why they've got this sort of a question, because their solution comes out really nicely if you follow the U substitution and doing it manually. So whilst you've got the CAS to check little bits and pieces, in reality it's a question you did by hand. As opposed to question 14, which was just straight under the calculator. Straight on the calculator gives an answer. So that was nice. 15, look, they're obviously similar to the previous ones. Look, there is nothing to say that you couldn't, well, not so much for 15, but perhaps for 12 and 13, evaluate them on the CAS and see which ones matches off. But it's time consuming, it's long, you don't have time for that sort of thing. So just again, that U substitution, the half, change your terminals. I guess in the specialists, they're really nice in that they tend to not muck around with the terminals and put a negative a half out the front and things like that. So, and then put a negative out the front and then swap the terminals and try and trick you up like that. I think they decide it's challenging enough as it is. And so, you sort of work through it as you expect through it, and often the answer that you expect to find is the one that's there. 17, again, that's just a straightforward repeated linear factor. So it'd be nice to see some more of them. 19 probably is more really next chapter, where we start finding the functions from the derivative, and we soon learn, I guess, that where we've got these initial values here, if you have a look at the theory behind it in here, obviously if we anti-differentiate the derivative, we end up with the function. So if I work out that gives me the original function, doesn't it, plus some constant c, which is what I wrote there, just the original function, f of t, which is the antiderivative plus a constant. And if you substitute in your t equal to 0 and what y is at the time, your constant is just 1 minus whatever f of 0 happens to be. So you can see in here that that's the format of my original function after I've done my integration. Then to work out the value of the function at a point, well, we just put that point in, don't we? We put x equal to pi on 3 in, and you end up with f of pi on 3 plus 1 minus f of 0, whatever that happens to be. A little rearranging, you get f of pi on 3 minus f of 0. Don't forget capital F is the antiderivative, which is the formal definition of what the integral is. So it turns out that D is the correct response. But as I was saying, we sort of do that a little bit more next topic. Again, another U substitution. Key being whatever you substitute U in for, its derivative needs to be there. So if we put U equal to natural log of x, as opposed to putting U equal to the natural log of x cubed, which makes things messy, the substitution for U is normally relatively straightforward. It's pretty simple. If U is equal to natural log of x, well then the derivative is 1 on x, and there's my 1 on x there. 1 on x dx. Put your terminal points in, 3 and 0, and works out quite nicely. Similar again for 22. Put U equal to tan inverse of x, and the derivative of tan inverse is 1 over 1 plus x squared. and there's my sort of 1 over 1 plus x squared dx. All right, and so it's this point here you know if you've got it right, because it should be a really straightforward du dx swap. Okay, again, put your terminal points in and we're away. Where are we up here? Again, just another u substitution, put u equal to the x squared minus 1. Again, not trying to take it, the u equals the square root of x squared minus 1, because again, the derivative, once we differentiate that, its derivative won't be present. So we just bring the dx across, take the 2 over, and we get a half du is x dx, and terminal points. So look, once you've done a few of them, hopefully they sort of become a very comfortable sort of fit. Something like this one, we've got f double dashed of x. I guess my initial reaction was, well, we've got f double dashed, integrate that to give me f dashed of x. But then I've got no information about f dashed of x, have I? So what do we do? So I guess I use this point here. If f of 0 is equal to 0, then only b or d satisfy that. So then, since we've got it down to a 1 in 2, if this is b and d, if either one of those are the function, if I double differentiate either one of those, it should lead me to f double dashed of x, which is written. So I've done it by hand there, d, and the only reason I picked d was because it was a bit simpler. So I thought, well, if I start with the simpler one, and if it doesn't work, well then b must be the correct one. But in reality, you just go straight into your CAS, differentiate twice and see if you get the answer you need. Another substitution, if you put u equal to tan, the derivative of tan is sec squared. Yep, so hopefully you're getting comfortable with that. So D. Okay, so now we've got a little bit of short answer stuff. Use calculus to find the exact value. So who knows where this was. If it wasn't tech-free, if it turns up in a tech-free, well, you're obviously going to have to show lots of working out to get all your marks. And if it is a tech-free, well, then you're going to approach it in this way. Again, it's something, the odd power of sine. So we know it's a sine times sine squared. Just be careful with you. I guess there's nothing to say. I reckon get into this habit of changing your terminals as you go, because as you saw from all those multiple choice questions, the terminal points need to change quite regularly. So if you're in the habit of changing them, that's what you do. You change your integrand into an integral in terms of u, and it should match off to an option. But just don't, when you're doing the writing, don't mix your variables. If you're working with the u, don't put the x terminals there. Okay. Again, just be a little bit hard to read in through there, but just be careful. Root 3 cubed is root 3 squared, which is 3 root 3. Over 2 cubed is 8, which is 24. I've got to say, I must confess, when I worked through it, I kept on making a mess of that in there somewhere. But got there eventually. What happened there? Hang on. Okay, again, another nice partial fraction. This one's leading us through it. Work out our partial fractions, get them into a form that's required. So perhaps we should probably have a box around that answer to say here it is. Hence write down an antiderivative of. So we've got our integral in the ax plus b to the n form. So whether you leave it in, whether I decide to leave it in there, but then change it into 7 on x plus 3, just in the last part there to work it out. To 3 significant figures suggests obviously that in this assessment task back in 2001, we didn't have we didn't have CAS calculators back then. But there's the exact form. So we could easily have this question now and just saying what's the exact form of, or leave it in the form a natural log b plus c or something. All right, question 6. Again, it's something that we tend to do more in, it's specifically addressed in methods, isn't it? Sort of that integration by recognition, work out a derivative and hence do the antiderivative. All right, so the first thing we needed to be conscious of in here is that root 2 is the whole function, the root 2x, not the square root of 2 times x. So that could have been easily a little error that we made there. So just be careful in here when you're working out the derivative of root 2x, so root 2 times x to the half. So I decided to leave it in that form there. Y equals sine inverse of u, so the derivative there is fairly straightforward. Product together sort of makes sense. I guess the two little tricks in here, that root x, the x term goes into there. Okay, they can share the same square root sign. So that's fine. And then just to finally get it, so that's a nice answer there, but we're missing a 2 from inside the rational, the square root rational sign. So if I simplify this, or if I break this 2 here into root 2 by root 2, then one of them will cancel, won't they? So what I'm sort of saying is that root 2 can cancel with that root 2, and then that root 2 can go in. And so we end up with the format that we require. And once we've got that, well, we've got dy dx is equal to. And look, and I guess the big thing is with the hence, you may not have been able to prove that part of it, and that happens. Well, you know what? You've got the answer there, so you can still come and go at this part here. We know from the question we were told that this is the case. Yes, we had to prove it, but we were given it to it in case we couldn't prove it. So we've got that there. Integrate both sides with respect to x. We get y equals that with respect to x. And that's the integrand that we're looking to evaluate. So all we now need to do is substitute in for the y, which is my sine inverse. Just be careful subbing your terminal points in, and I think that works out reasonably well. Times everything is 0. I've lost our page. What's happened? Another one of those ones where it's probably more next topic in that we've got a derivative function. We need to find the original function, but that's okay. So I decided that I would take 15 and bring it out the front. We've got our normal u substitutions in here. Don't forget that little negative for du dx. So I've got that negative du out the front. Negative du was dx. We've got my u to the half and 2 minus u substitutions for x. Remember, rearrange x there to get x equals 2 minus u. And then I can just multiply that square root sign through. So we end up with an okay sort of antiderivative there, and then integrate that. We end up with a reasonable sort of integrand expression. I decided that I thought it might be easy to simplify everything first. So I got the common denominator with 3 and 5, cross multiplied as you do, negative 15 out the front, and I guess that's why I thought that common denominator now would be a good idea, because they'll cancel. In here, I thought it happens all the time that if we have that fractional power, 3 on 2, 5 on 2, or a half, a negative a half as powers, we take out the smaller power as a common factor. So we do that often. So I thought, well, I'll do that in here now and take 2 minus x to the 3 on 2 out as a common factor to leave me with the 10. And if I put the power in, that 2 minus x is really 2 on 2, isn't it? So that's a 2 on 2 there, because 3 on 2 plus 2 on 2 is the 5 on 2, and you add the indices when you multiply the bases of the same. So from there we can simplify that expression, and we sort of get that 3x plus 4, 2 minus 2x, etc., plus c. and it's now I decided to substitute the C value in, and it would have worked out probably just as easily. But at x equal to 2, that 2 minus x to the power is going to be 0, 0. There we go. 2 minus 0, so, you know, it probably still would have come out. So C is 0. And the only other thing, I did have a negative 2 out the front. I need to multiply that back in to get it into the format that we require. And there's my A equal to negative 6, B equal to negative 8. All right, 16, 1 plus x over 9 minus x squared. First thing, I guess I must confess, the first thing I looked at, I looked at the 9 minus x squared and was thinking a squared minus x squared and thinking tan inverse. But fortunately, soon realised that tan was at a squared plus x squared. And instead we've got linear factors on the bottom. So partial fractions, go through the process, cross multiply. My respective a and b terms were 2/3 and negative 1/3. Just make sure you've got them on the right spot. Just be wary of negative signs where they are. So because each of them has a negative, we end up with 2 negative log expressions. So I thought, well, if we bring the third out the front and that 2 can go up as a power, when we add bases of the same power, we multiply the terms. So I thought that was a nice final representation. Although I must confess it doesn't look exactly like a negative sign there. So make sure it's clear, negative 1/3 natural log. All right, getting towards the end. Same, another straightforward substitution, isn't it? We've got cos squared and a sine. Angle, size of the angles are the same, so it's a straight. U equal to cos to u dx equals sine 2x. Just be careful of the regular things that you need to be wary of. Negative signs, we've got a negative 1/2 there, so put the negative 1/2 out the front of your integral. Get your terminal points sorted out, put them in the respective spots, and we end up with quite a nice integrand there in terms of u to work out. And just be careful with negative signs, and away we go. Well, that's it from me. This one here, go to that Edrolo link, and our old mate there goes through a really nice explanation of this problem. So I don't think you need me to do it as well. Tech Active, talking about points of inflection, which we've covered, points of inflection, etc., etc. I guess maybe stop here. Okay, off we go. The only thing just to be conscious of is in here, question C. We haven't, you'll still go through the answers, but we haven't done any volumes of revolution and things like that. We didn't even touch on that last year. So perhaps, I think you can probably stop at that point there. Not yet, not yet. Jesus squared, the formatting didn't work out too, did it? And not here, yeah. So maybe